I'm Paul Friedlander with Carollo, and the idea today is to just give an overview of the DERWA Phase 2 facilities. So am I on screen here? There's been some training on the polymer feed system last week and on the coagulant pumps and the transfer pump. There's going to be specific training on, especially on the ballister flocculation, the active flow process, and on the UV. So the idea today is more of an overview of the whole treatment process, how things fit together, and then again with more detailed training on specific, on especially UV and active flow coming down the road. Feel free to ask questions, comments, any point. The whole idea here is that this is an interactive. It's not just me up here blabbing away, but an interactive session where the whole purpose is for you guys to understand the system better, and yeah, if there's any comments as well. All right, so do I point this over here? There we go. All right, so I want to start with the project objective, since it is Valentine's Day today. I'll put that in those terms. The idea is that you guys love DERWA Phase 2, that it makes your lives easier. And I think, I certainly hope that it will do that. This is the basic treatment train for the active flow SFUV. And this is what there's different words you'll hear me using for this, but this is the treatment train that includes tips, new band screen, the ballister flocculation process, filters, UV, and pump station R1. And I'll be going through those one at a time in terms of process capacity for each one and how that fits together. You will also still be able to operate the existing train, which maybe I'll be calling DERWA Phase 1 here, going from tips, existing band screen, filters, UV, and pump station R1. And this, what words you use for these two different treatment trains is really up to you, but I'll be calling this train direct filtration SFUV. And the word direct filtration comes originally from drinking water treatment, where direct filtration is with no solids removed before the filters. So it's going directly, all the solids are going directly to the filters, as opposed to a system where you're settling out solids before the filters to reduce the solids load. Okay, so for DERWA Phase 2, the capacity, the recycled water production capacity is 16.2 MGD. So that means 16.2 MGD to be pumped out to distribution as a maximum daily flow. So at this point, I just wanted to go through each process, so starting with the tertiary influent pump station. So what capacity is needed for tips for 16.2 MGD recycled water production? Is it 16.2 MGD? Right, we need more than that. So the tips flow needed to produce 16.2 MGD. I'm going to start over here. We want 16.2 MGD out to the system. The UV, all the water that comes into the UV comes out of it. So we just need 16.2 going into the UV. But the filters, of course, are a different story. We've got waste backwash, and the assumption here in the design is that we have up to 1.8 MGD of waste backwash. That's 10% of 18 MGD going into it. And so it's sized based on that. The active flow as well has a waste stream from the clarifier. And it's designed for a maximum waste flow of 0.4 MGD for the active flow. And so we need 18.4 MGD going into the active flow to get that 16.2 out the other end. The band screen also doesn't really have any waste. And so the capacity we need for tips to produce 16.2 is 18.4 MGD. Again, we're using these assumptions. We've got 10% waste backwash here. With the active flow in operation, you can probably reduce this significantly in terms of the percent waste backwash. But that's something that, we want to make sure you have flexibility of up to 10%. there. All right, so the existing system, we're going to call in phase 1. There's 2 duty pumps for tips and 1 standby. The change with phase 2 is we're adding an additional duty pump. So you have 3 of the same size pumps for duty, and then a 4th the same size as a standby. And this hole is designed for a flow range from 2 MGD up to that 18.4. But we want to operate below 2 MGD. We want to be able to operate down to 1 MGD with SFUV. I know you can't do that now, but the idea with DERWA Phase 2 is that down to 1 MGD, you'll have the option. You can run MFUV or you can run SFUV. And so there's a 5th TIPS pump that can operate between 1 and 2 MGD. There's no standby for this pump, but the idea is if you want to operate in that lower range, then you'll run this pump, because these pumps could potentially be damaged if they run below 2 MGD. The manufacturer doesn't recommend operating them below that point. All right, so that's TIPS. I'm going to move on to the band screen. So as we talked about before, we need 18.4 capacity, 18.4 MGD capacity for the band screen. And this is a new band screen, so you'll have a total of 2 band screens. There'll be 1 band screen going to the active flow and the other band screen, the existing one you have out there, if you're running direct filtration. The decision was made to size the band screen for the ultimate, which is DERWA Phase 3, which may or may not ever be needed. But the idea was, if we're putting the band screen in now, if we do want to have DERWA Phase 3 in the future, which is up to a recycled water production rate of 19.4 MGD, we might as well make the band screen a little bit bigger, so we can do that now. We've done the same thing with the active flow. It's also the active flow structure. It's hard to make the structure bigger once you build it. And so that's also designed for that DERWA Phase 3 flow rate. So this band screen, and this is in the channel going to the active flow. It's got a 7.5 foot width. So it's bigger than the existing one, which is about 5.5 feet. It's the same type of band screen, same manufacturer, but it's a wider band screen, 2 millimeter opening size, which I think matches what you have out there now. And with a 2 horsepower motor, I think it's 1.5 horsepower for the one you have there. So it's a bigger unit, but again, it's the same type of band screen and manufacturer for the existing one. Any thoughts or questions so far?
And it is headworks, right?
Yes. Yep.
Oh, like Dead Bath and Beyond.
All right. Well, I want to talk about active flow. And so this is the biggest piece of DERWA Phase 2, it's the treatment process that you don't have now that you will have with DERWA Phase 2. And yeah, basically the ballast flocculation. So active flow is the brand name. The type of process is ballast flocculation. So you'll hear me using both of those terms, but I mean the same thing when I say ballast flocculation or active flow. So the ballast flocculation can buffer variations in secondary treatment. So now I've changed this from TIPS up here to secondary treatment. What active flow can do is, if you have problems or hiccups or whatever in secondary treatment, active flow can make it so your tertiary treatment process can still run very smoothly. And so it's kind of like, active flow is kind of like the superhero of the treatment process. And again, so the idea being that you can, I've got the secondary treatment can be going sideways, and you can still, that's the only trick thing I have in the slides, is that, you want to see that again? There you go. So I want to get into some of the details of the active flow. This little cartoon shows the main 3 process units in the active flow: the coagulation basin, maturation basin, and the clarifier. And we'll be going into a lot more detail on that with the Kruger, with the active flow training a little bit further down the road. But in terms of capacity for the active flow, whoops, it's still going back and forth. There we go. Okay. The active flow ballast flocculation consists of 2 parallel treatment trains. And so for the DERWA phase 2, for that 18.4 MGD, it's 9.2 for each, going through each of these trains. That is at a loading rate of 25 GPM per square foot, and that's the loading rate for the clarifier, which is this part of the treatment train. As I mentioned before, the structure is designed for DERWA phase 3 because it made sense to make it a little bit bigger to be able to handle that future. And so it can hydraulically and in terms of process-wise can handle 22.2 MGD at a slightly higher loading rate of 30 GPM per square foot. But it should operate well in both these ranges of loading rates. All right, so what happens, what if one train is out of service? So for some reason, it's the middle of the summer, and something happens so you can't run this train. Each train is designed, let me go to the next slide. The system is sized hydraulically for 75% of the ultimate flow through one train, which is 16.6 MGD. So hydraulically, it can handle 16.6 MGD through one train. Process-wise, this is only in extreme situations where, again, you need to produce the water, and you don't have the other train in operation. So at the 16.6 MGD, it would be at a loading rate of 45 GPM per square foot. And so you wouldn't get as good treatment at that kind of loading rate. But again, it's just, so you have the idea is so you have flexibility to operate this in different modes if you need to, because you've got problems. So the whole, you'll see as we go through this with the active flow, there's a lot of built in there, so there's flexibility in the operation, because that will be a key part of making sure whether there's secondary treatment process problems or mechanical problems, that you be able to run the tertiary treatment plant smoothly.
Is there a minimum flow rate through it for it to be effective? Or?
That's a perfect lead into the next slide, Jerry. Thank you. I appreciate that. But you don't have the next slide. I just added it in there. But the next slide has to do with if you run it at low flow rates, it'll work fine. At lower loading rates, the clarifier, at 15 GPM per square foot, for example, it's going to probably operate better in terms of the settling than it does, higher loading rates. At low flow rates, you will get higher rates of waste because of so the ballast and flocculation waste varies with the flow rate, and that has to do with the pumps that pump out of the clarifier. They're constant speed pumps, and they need to be because they're taking sand as well as the waste. And so if you're at low flow rates, and you can see here between 0 and 5, let's say you're operating it at 2 MGD, you're going to have a higher rate of waste. And this, I know many of you don't know what this HCS system is. It's a sludge concentration system. This stands for high concentration sludge, and we will review that when we go through the active flow. But this chart is without this HCS system. With the HCS system, all these numbers will come down further. But what this shows is that, so when you're running one of the sand pumps, which pumps out of the clarifier, if you're running it right about 5.5 MGD, then it's at its most efficient because it's a constant speed pump. If you're lower flow rates, it'll operate fine, but you'll have a higher rate of waste. Once you go over this amount, you turn on a second sand pump, and therefore the percentage of waste is higher until you get to twice this flow, where it goes back down again to around 3%.
So my question was, so you got the one pump that does between 1 and 2 MGD, right? The small pump?
Right.
So is that that's where the efficiency will kind of go away then, as far as?
So you were asking about the efficiency for that pump pumping in.
Pump pumping, right.
That pump should be fairly efficient over that range. It's just a 20 horsepower pump.
Okay. But as far as the
So for balance and flocculation, the other thing is, if you go low flow rates down this way for balance and flocculation, for example, there's a rapid mix pump. that is designed to pump about 5% of the total flow back to mix with a coagulant. If you get in lower flow rates, it'll be more than 5%. But it's still, again, it'll operate fine.
So would the idea be for that small pump to go direct would be the other option? Or would
You could- you-
balance it?
You could do it either way. Yeah. I think originally the idea was that for the low flow rates that you would go to the direct filtration, but it'll allow you to go either way. Yeah. Does this make sense why it's shaped that way? Because again, this is with one sand pump on, 2 sand pumps on, 3 sand pumps on, 4 sand pumps on, and there's 3 sand pumps. There's basically 2 duty and 1 standby pump per train, and so at that, the most you'd have on if you're operating both trains would be 4 pumps. So you'd be out here. This is the 22 MGD, again sized for this. The decision was also made by the district for the sand pumps to size those for phase 3 because it's not that much more than phase 2. All right, I'm hoping that for a lot of this stuff, again, the idea is not that you just see this stuff today and then we're done and you have to go out and operate the thing when it's built. We're going to have a series of training. Yeah, Sean. Yes.
At the other end, at the other end of perspective, you talked about each train is designed for 9.2, but ultimately they could do, that would be 11.1.
Right.
So theoretically, you should be able to run 11.1 MGD through one train.
Yes.
And expect to get pretty good.
Right. I guess I assume where you're going with that is if you have 10 MGD, do you run 2 trains or 1 train? You can go either way. If you run 2 trains, you're running more equipment. But you also, if you have 2 trains, you're operating at a lower loading rate in the clarifier. So with experience, you can kind of gauge that the better performance that you might get versus the equipment for those kind of things. Yeah. Yes, Jeff?
You probably answered this in the preceding slides. However, is there a chart that shows the TSS concentration versus the performance of each train versus the light output wattage used for the UV? So it shows which one's most effective to use.
You're saying the trains of the active flow?
I'm sorry, yes, for the active flow. So the secondary clarifier effluent,
Yeah.
that value of TSS concentration in relation to the performance of each train as the flow goes, what's most efficient because due to the outcome of the UV wattage output. So, you know what I mean? Which is
Right. Yeah, it's a little hard to make. You got to make a lot of assumptions to kind of come up with that because this is taking solids out, which is going to increase the UV transmittance, but it's not necessarily, reducing solids 1 milligram per liter is going to increase, say, UVT by 1%. And so I think that's something where, probably with operational experience, you can kind of gauge if you like this example of if you're at 10 MGD, if you run 2 trains instead of 1 train, what does that do in terms of UVT? Yeah.
kind of a startup pilot, I guess.
Yeah. All right. So I want to move on from there to the filters. And the first thing to know is that there are no filter modifications in DERWA Phase 2 to increase capacity. So the only change in the filters is the header in each filter there was additional bracing added for earthquakes, but there's no process changes in the filters. So did we just forget this and we need to add it in now, Robin, or did we? Is there a reason for that? All right, the original filter design, so what you have out there now, it was designed for 4.7 GPM per square foot loading rate for the filters. And as you know, this is not something that the filters are actually able to do. It's, I don't know what they're awfully, I think they're generally loaded up to about 3 GPM per square foot. So that was one of the reasons for adding the
That's around 2 mgd load flow rate.
2 mgd
Filter.
for each filter. You're saying it for the existing filters? Yeah, okay. Now, Title 22, the recycled water regulations, allows filters to be operated up to 5 GPM per square foot without regulatory testing. And so that's so the filters can be operated up to 5 per Title 22. And so the idea is that the filters to be operated up to 5 GPM per square foot until regulatory testing is performed at loading rates over 5 GPM per square foot. And I'll explain that a little more in a minute. But first I wanted to ask the question, what does this mean for filter capacity if we're operating at 5 GPM per square foot? And the reason that that suddenly we can operate at 5 GPM per square foot from a process point of view is that with the active flow, you'll be getting much lower turbidity. The turbidity should be able to hit 2 NTU coming out of the active flow, and therefore the filters should be able to easily handle the 5 GPM per square foot with the active flow running. And so what does that mean in terms of capacity? The filter capacity at 5 GPM per square foot is 11.7, assuming 10% backwash. And these are the only calculations I have in these slides, but for those of you who like calculations, here's the 5 GPM per square foot. We've got 6 filters. Each filter is 300 square feet. We have to subtract the backwash because in terms of what we're actually producing from the filters, because the loading rate is what's going into them rather than what's coming out. And so that's how we get, with 10% backwash, 11.7 MGD. As I mentioned before, with the active flow, we should be able to reduce this amount of backwash a lot. And the way that's done is by raising the weirs on each filter in the backwash chamber. And so if we assume 5% backwash, then the filter capacity goes up to 12.3 MGD at 5 GPM per square foot. And this is just the same calculation there. Why is that important? What it means is that 5% backwash is probably something that can be achieved with the active flow. And so basically what this means is the plant should be able to operate, the filter should be able to operate up to 12.3 MGD once the active flow is online. And I think that's more than we have in terms of flow right now. And so it's not 16.2, but basically the capacity of the filters will be increased once the active flow is online. But of course, we want to get to the capacity for the rest of the treatment plant. We want to get to that 16.2 capacity. And so some recycled water facilities in California have been permitted to operate up to 7.5 GPM per square foot after regulatory testing. And so if we operate at 7 GPM per square foot, then the DERWA Phase 2 facilities would need to operate up to 7 GPM per square foot to achieve 16.2 MGD with 10% backwash. And so this is the value that we'd need, again, making a conservative assumption about the percent backwash, that this is the loading rate we would need to achieve. That the regulatory testing is something that would happen probably not this summer when you have to make sure you're producing recycled water, but perhaps this winter. And basically what it would involve would be putting a plan together, sending it to the regulatory agencies to be able to operate the filter at different loading rates, see what the turbidity is, just basically to show that and we'd probably test it up to 7.5 because just to get maximum flexibility, but the testing would be to demonstrate to the regulatory agencies that we can operate at 7.5 or 7, whatever we decide it's going to be, and still produce the recycled water at the right quality.
But the turbidity requirement would be lower on that based on what's been done at some other systems.
That's correct. Operating above 5.5 GPM per square foot requires meeting the stricter turbidity limits. If we had practiced this, we could have done better, Levi. So yes, your existing limits are 2 NTU, 24-hour average turbidity, 95% of the time, less than 5 NTU, and never over 10 NTU. If you want to operate over 5 GPM per square foot, then the requirements are likely to be 1.5 NTU, 24-hour average, 2.5, 95% of the time, and never over 5. And if you're wondering why this is different than this, I think it's an excellent question. The answer, as far as I know, is that the first agency to go through this, which was the Monterey Regional Water Pollution Control Agency, when they were doing their testing over 5 GPM per square foot, they wanted to produce the best water they could just to make, to show this is going to work really well. And so they dialed it in really well, and they were significant. They were always under 1.5 NTU. And so the regulatory agencies said, "Oh, great, we're going to give you this as a limit." But now the different agencies that have gone through the testing, and there's been 4 or 5 now, they've all gotten these limits, and so that's kind of the precedent, and so that's what we would expect that you'd have here. No, I talked to them about it, and they said, "Boy, we wish that when we had done the testing, we'd dial it back just a little bit, so we were just barely meeting these limits." But anyway, it is what it is. And so it's not a matter of, if you get the regulatory approval to operate above 5 GPM per square foot, it doesn't mean you have to meet this all the time, only when you're operating above 5 GPM per square foot. All right.
So are you saying that the things would change then, as you go under and over 5 gallons per minute per square foot?
Yes. Yes, and so what Monterey does, they thought they were going to need to operate over 5 GPM per square foot. Their flows have gone down, the flows to the treatment plant, and so they don't have enough water to operate, generally speaking, over 5 GPM per square foot. And so they try to not operate over that so they can just meet the 2 NTU. Because obviously if you were going back and forth, it would be a little difficult. Yeah.
We'll just do the lower one all the time.
Okay. They don't have an active flow. All right. Now I want to talk about UV. So the existing system is permitted for 9.7 MGD. There's 2 UV channels, as you can see here. There's 4 duty and 1 standby banks, so you've got the 4 duty banks and 1 standby per channel. There's 6 UV modules per channel, and that's what these lines are here. That's the 6, and so this is a module. So this is looking down from above. You've got the 6 modules. There's 20 lamps per module for a total of 1,200 lamps. The original system was designed with breakout walls on each side of each channel, so you could knock out one or both walls and add modules. And so that's what, for phase 2, what we've done is taken out the wall on one side of each channel to put in, instead of 6 modules, to have 7 modules. And so we've got 2 channels, the same number of banks. We've got 7 modules per bank, same number of lamps per module for a total of 1,400. And with the testing that was done last year, just by adding 200 more lamps, the capacity went up from 9.7 to 16.2. And part of that was that the system will be operated based on UV intensity in the future, which is different than what it is now. And so the plus side is you get a lot more capacity and more energy efficiency, because you won't have to turn as many lamps on. The complicating factor is that we have to make sure that those UV intensity sensors stay clean and calibrated, so the system can operate properly. So the actual capacity, let me go back here. So again, you've got 16.2 MGD. The actual capacity of the UV system depends on water quality. Walk over here now. So for example, 16.2 MGD, and this is just based on some calculations. It might not be totally exact. With both channels on, 100% power. If you have all 4 duty banks on, this is the regulatory dose needed, 100 millijoules per square centimeter. You can do that at 54% UV transmittance or higher. Where actually the system's going to shoot for 105 millijoules per square centimeter, so you have a little bit of a buffer there, and you'll need to have 55% UV transmittance to do that. But if your UV transmittance is up, say, at 64%, you can get by with having just 3 banks in each channel on. And actually, although the system, the idea was to be able to hit 16.2 MGD, which is DERWA Phase 2 flow rate, the system is approved by the health department for 17.6 MGD, and which means that again, you can see, for example, at 57% UVT, you can actually get more flow through that. Now, that's not important in terms of the total flow through the system, because you're only going to be permitted for the whole system at 16.2. But the advantage of that is that you can put up to 8.8 through one channel before you have to switch to the other channel, as long as the UVT is high enough. So and the system will calculate that. All right. Yeah, I kind of figured there'd be more discussion. Yes?
You said before that it's now controlled by intensity. You mean dosage, or?
It is by dosage. And the dose is calculated based on the intensity and the UVT and the flow rate.
So it's dosage, not intensity.
It is.
Right now, we have to have a certain amount of lamps on for a certain amount.
Right. It's based on flow. Basically, the parameters right now are UVT and flow, right? Just those two. Yeah, that doesn't, yes, right. That doesn't control how many lamps are on, but if you get below that, then it'll have to turn another bank on, right? But in terms of...
So if you go by dosage, your number of lamps can vary as long as the intensities are compensated. So
yes, there's still...
less lamps, but higher intensity, and still have the same dosage.
Yes, yes. And the range of UV intensities is higher, is wider than it is now. You can go down to 0.77. I think now at 1 point something.
So we're gonna monitor dosage.
Yes, it'll be monitoring dosage. Right, but if the intensity sensors aren't clean, it's going to calculate a lower dosage.
Okay.
Yeah, but you're right. It'll be based on dosage. That'll be the.
So it's going to if it bypasses, it's going to bypass on dosage, not intensity.
If the intensity gets below 0.77, then it will not count that bank. So I think that number right now is like 1.19 or something.
Yeah.
And so it's a much lower number, but there still will be a number where if it gets low enough,
But actually at 1.19, it fails.
that bank fails, yes. So the bank will, yeah. And I think by failing, what it means is it turns another bank on, right? It turns a standby bank on. Yeah. So you'll, right, so there'll still be a low intensity which will fail the bank, but it'll be a much lower. I mean, it seems like it gets triggered a fair amount now, and that should not happen very much as long as those sensors are kept clean and calibrated.
So the new regs, it says measured UVT is used to control the power to the banks to achieve the target intensity. So it's so the
UVT is a factor as well.
function of, so the UVI we're getting is not the direct reading, it's directly related to the UVT.
The new system, the new system is going to take into account UVT and UVI and the flow rate.
Yeah, so the UVI is not the direct reading to control the dosing?
It is. If everything else is the same, the UVT and the flow rate is the same, a lower UVI will mean a lower dosage. That's providing a lower dosage, a higher UVI. So it's taking both UVT and UVI into account.
So we need to. So the importance of calibrating the UVT is in.
Yes, that's important as well. That's important as well.
It's a calculation. The dosage is a calculation.
Including both of those. Yes, yes, yeah. And we had, I don't know, for some of you were here. We had a meeting in December going through some of the details of the UV dose calculations. And we can certainly do that again. And also, the UV manufacturer will come and will give training on those specifics. But yes, you're right. It will be, the UVT is going to be just as important, but UVI will be more important than it has been.
Conceivable if we had a 75 UVT that you could only run 3 banks instead of 4 banks.
Yes. Yes. Yeah. Now it was tested on a certain UV range, UVT range, and so if you go, I think the max was 72. So if you're above 72, I don't think you get any further credit.
The actual control scheme of the reticle will be based on dose, and give us a dose, and if it's, whatever, gets close to the low dose, will it increase power first or increase length?
It will, well, yeah, first of all, it'll have power go up to 100%. So, yeah. And that's, like I said, we can go through that again.
Then it'll start over again, go back down to low power, and come back up again.
I think it starts at the high power and then ramps it down rather than the other way around. Yeah.
Right now, everything is just 100%, right?
Right, yeah, the power doesn't go into the
They still use, it still reduces power. Still goes down to 50%.
Right.
If it can.
Yeah.
Just based
Yeah.
on the UVI.
What is UVA, the absorbance?
UVA,
Measure UVA is used to control the number of bands. So it's not the UVI, it's the UVA absorbance.
well, the absorbance and the transmittance are mathematically related to each other.
Yeah.
And so when you see UVA, it's
Same as intensity.
the same as, well, it's measuring the same thing as UVT.
Transmittance. So,
Sorry, that makes sense? Yeah. Yeah. Anything more on the UV? Like I said, we'll have more specific stuff on this. And like I said, I think you're going to be happy with the reduced power use, but in terms of keeping those sensors clean, that'll be more of a concern than it has been.
So additional ballast for all the new lamps modules, right? Additional ballast put in,
There's ballast for the new modules.
Right.
Yes.
more heat.
So there was real estate in each cabinet.
Right. Yeah. So it was. The cabinets are sized so you can put it. So we got 7 modules per bank now. They're sized for an 8th one as well in the future. Yeah.
And there's more sensors now than there were with the old system.
No, there's no more sensors being put in because you only need 1 sensor per bank.
There's more sensors because there's more banks.
No, there's no more banks. You just have 1 sensor per. So you got a total of 10 now, 10 banks. Yeah.
And the sensors are not calibrated, they're just certified correct.
There's supposed to be some,
They.
read something.
Yeah, I mean, you need to send them back. You need to send them to Wetico to get them calibrated,
Yeah.
or
Or they
Which
don't
means we
meet
probably
by-
need some.
or certified. Or
Certified.
yeah.
You get a piece of paper that says it reads this when it should be this, and it's like within 0.01% or something.
But also, though, you'll have a calibration sensor. You'll have to swap out the sensors and to see if they're working properly. That's part of it, right? In other words, you'll.
Yeah. There's one sensor that's supposed to be calibrated so you can check the other one against it by just swapping them out.
it's a baseline for a reference.
As a reference.
Explain that a little bit more.
There's no calibration.
No.
It's just,
It either
It's
works or
not.
doesn't work.
it's either with.
Yeah, I guess. Yeah, I hear what you're saying. It's not. You're not actually calibrating. You're saying, okay,
Check it.
this. You're checking it. Is a better. Checking is a better word. That's really what you're doing is checking it. Yeah. Yeah.
Can I ask that if you make any comments or questions, that you could speak up a little louder?
I totally forgot about that. Sorry.
So again, I mean, just how is that going to explain a little bit more in detail how that sensor check is going to work in the field from a practical standpoint? So you have one in there, you take it out, put one in that you know is calibrated, and what do you do? Look at the reading that it's getting and seeing if it's the same or?
Yes. I don't know what we talked in December. I don't remember the detail in terms of what % is okay and what's not okay, but yes, that's basically the situation. Yeah.
But if you send them back to Redico, they have a known.
Right, they're actually checking to see if it's correctly reading.
It's not checking against another sensor, it's checking against their apparatus.
Yeah.
Certifying.
Yeah.
Buy one of those?
So it's different. That's got to be done annually? Or is it?
In terms of sending them back, I think that you send it back if it doesn't check out. I don't think you need to do it otherwise. But I'd have to go back and look at those details for that.
I thought it said you check it monthly against a known sensor.
Right, yes.
And then you certify them annually.
That's what I read.
Is that right? So it means you have to send it back annually, okay.
Well, then we gotta make sure.
Probably going to need more
We've got
than
a
10
replacement.
sensors.
You just send them all back.
Send him all.
Yeah.
So for the flow chart, like the control bank flow charts we have, so are you providing us or the Redico will provide us? Because we increase the flow and like the minimum, we increase the capacity. So remember that we have like a flow chart that we are like.
The quick, yeah, right.
So
Much flows, so many things.
That's something that, yeah,
That's pretty much obsolete now, right?
the existing way will be. It will be. The flow chart you have now will be.
But will there be say a minimum number of lamps per
Yeah.
flow?
Minimum, it will depend on,
So there won't be. It just depends on dosage.
well, if a certain number of lamps are out in a bank, and I think it's 4 lamps,
yeah,
then that bank,
Count that being. anyway.
right.
is that
Yeah.
number of lamps or percent of the total number of lamps?
I think it's, I don't remember those, I think it's 4 lamps, but I need to check that. Per bank.
They can't be next to each other too, right?
I didn't read that next to each other. It's just like a percent.
It doesn't say.
Yeah.
And we can pump the 1 MGD through these then?
Yes.
Okay.
There's actually, in the letter from DDW, it doesn't say anything about a minimum flow rate. It talks about the 17.6, doesn't say anything about a minimum flow rate. So you can certainly go down to 1. And if you go down below 1, I mean, TIPS is designed to go down to 1. Can you bring it down a little below that? You probably can. You know, I mean, it's yeah,
With the backwash and it'll be less than 1.
yeah.
Tips is 1.
10%.
Yeah. All right. Yeah.
The reference sensor has to be sent back annually,
Annually? Okay. Thank you.
and the duty UV
Okay.
is monthly check.
Okay, so just that one sensor has to be sent back annually.
More sense. Try and send that over back.
Okay. And the Title 22 tertiary recycled water coliform standards still apply for your UV system. The 2.2 MPN per 100 mLs for 7-day median, less than 23, no more than once in a 30-day period, and never less than 240. So that's not changing. All right, so the last piece is pump station R1. So right now, there's 2 duty pumps and 1 standby. We're adding 2 duty pumps for this, so there's 4 duty pumps and 1 standby. And the flow range for this is between 2 and 16.2 MGD. You'll get more than 16.2 if you turn 4 pumps on at full speed. But again, the design is so you put out 16.2 because at the end of the day, the facility will be permitted for that 16.2 flow rate. And you may notice, well, wait a minute, this is 2, but we talked before about 1 MGD, putting 1 MGD through the system. what this means is, again, this is based on the manufacturers not recommending flow much below that. And so the idea here is that you can operate the wet well for pump station R1 in two different modes, constant level or fill and draw. And I guess you normally operate in constant level, as I understand it. So when you get down, when you want to go down lower, you'll have to change that, or else potentially damage the pumps. So if you're operating at say 1 MGD, you got to let more water get in there. You pump it down at 2 MGD, let it fill back up, pump it down at 2 MGD, and so forth. Okay, wanted to go through anticipated initial permit treatment parameters. We talked about most of these, but I just wanted to kind of summarize them. So the idea is to request that we be permitted up to 12.3 MGD initially, before that regulatory testing of the filters takes place. For the UV, we still have the 2.2 total coliform and 100 millijoules per square centimeter, although, as I mentioned, this is you can adjust it in the UV controls. The idea is that that'll be set at 105, so you have a little bit of a buffer, but that you'll be able to change that if you like. For the filters, 2 NTU remains the same, and then the 5 GPM per square foot. So if you didn't have that in front of you, I was going to ask you, what are the permit parameters for the active flow? Like if you look at the page, you know the answer. And I did want to emphasize this, is that you got permit requirements for your whole facility. You got it for the UV, specific treatment requirements. For the filters, there's no regulatory requirements for the active flow. It doesn't mean that you don't want to operate it well. Of course you want to operate it well. But there's no, you don't need to put out a certain NTU or have a certain water quality coming in. The flow rates, I mean, it's not, it's just pre-treatment for the filters, but there's no regulatory requirements for that. Advanced green.
And that if you, I mean, we're not set up to do this, but if you could get the active flow effluent to 1 NTU, you would still have to send it through the filter. You
would, yeah. The regulations require for recycled water that it be filtered.
I was going to get it back up to 2.
They,
Clean the filters out.
they want a physical barrier, and that's why they require filtration.
We still have the 5 NTU more than 5% of the time within 24 hours period, right? For the permit?
That'll stay the same
So
until you go above 5 GPM per square foot. So if we're going back to...
so we still have that time frame, but we're still not bypassing if we go above 2 NTUs, but not more than 5% within 24 hours.
Yeah.
Yes, you have the same limits up to 5 GPM per square foot. Right. 2 NTU, rolling 24-hour average, and 5% of the time you can go over 5. Yeah. Yeah. But then when you're operating above 5, then those numbers will change. With active flow, yeah, you shouldn't have to worry about this at all. You certainly shouldn't have to worry about this.
Well, Paul, I think that's a good point to illustrate is the reason active flow is there is give you relief on the secondary. So it's designed to go up to 12, take 12 NTU in, and still get down to 2 NTU out.
Wow. Could we directly send it to the
it's like get rid of
the channel?
Haven't said that.
Design. I didn't say what do we need secondary?
To what channel?
The UV channel.
Active flow. Well, that's what Levi was asking about. Yeah, you can't. You have to filter. The regulations require you have that physical barrier. And I think part of the concern is something could flow through here, but you can't. Yeah, get through the sand. Yeah.
And all those new permit parameters also for direct filtration, the same permit.
For the 2 and the 5 and the 10, right? I don't think you won't be operating above 5 GPM per square foot at the with direct filtration. I think you'll still be in the same boat now where you'll want to have the loading rate quite a bit lower to make it work. So when you're...
I mean, is the possibility of going through direct filtration at 16.2? That's not, is that
No, that's not. I mean, that's not the idea at all. The idea is that direct filtration, and again, there's no. You can use it however you want to use it, but I think in general, the direct filtration would be something you'd use at low flow rates in the wintertime, if at all, and not during the. I don't think you'd be using that during the summer at all.
But if we lost the ballasted flop for some reason,
Yeah.
I mean, that'd be...
Right, you can lose a train and still go through the active flow, but yeah, if you lose both trains, then you're back where you are today.
Is the band screen absolutely necessary, or is it, how about if it went out? So you only have one band screen feeding the system.
The band screen, there's no regulatory requirement for the band screen.
So if that went out, you could still go, I mean, stuff would still go in, you'd have...
You're talking about-
going into the active flow you wouldn't want going in there, right? Because it wouldn't be...
Yeah.
Two separate band screens, though.
Right, you're saying
Well, I'm saying if you lost the band screen for the active flow,
right. If you lost it,
would you want to bypass active flow and go direct while you fixed it? Or
How long it will take to...
yeah, I think it depends on how long. Why is it down and what's going on with it? That's I think what it would depend. But because you could, I mean, you don't have to have a band screen to go to active flow.
But there's two separate band screens. There's one on the active flow, the new active flow facility.
Right. But that's what I'm saying.
There's the existing band screen.
But if that active flow band screen fails, you want to go into active flow, the new one.
Yeah.
You could bypass
Okay.
it, or you could...
I mean, you wouldn't have a band screen feeding before the active flow, right?
Correct.
Because you can't take and feed it to the other band screen.
And then go to active flow. No, you cannot. No, you cannot. But again, the active flow will work without the band screen.
But whatever that caught will now pass through and go on to active flow also.
Yes, and probably pass pretty much through and go to the filters, I would think. I mean, certainly the fruit labels would.
Right.
The heavier stuff, yeah, could come out here and then be in the waste stream.
But not that it ever happened here if we lose the flow meter.
On the question about direct filtration, I mean, I anticipate that it's going to make everybody's life easier once you get the active flow online, and you'll just probably leave it online all the time. But technically, like one of these days, if the chemicals for running the active flow were really, really expensive, and like Z's running the plant and he wants to save on chemical, he could bypass the active flow and go directly to the filter if he had 2.5 NTU coming out of the secondary element. He could.
Well, he's only trying to make 6 MGD, or something like what we normally make now anyway.
But, catastrophic things, one thing, like, we lost the TIPS flow meter a while back. We had to kind of make that thing work. If you lose the flow meter going to active flow, then you got a problem, because you can't flow pace anymore.
If you lose a flow, yeah, you'd have, right, in terms of chemical feed,
Yeah.
you'd have to figure out, yeah.
I'm just saying, there's circumstances where, but then the
Right.
side of the plant will be adjusted accordingly from the filters on for the direct flow,
But if you-
permitting and going.
Yeah, if you were going through this train, you didn't have a flow meter, I mean, I think you'd probably say, okay, we're running 2 TIPS pumps at 80%, and we know from the past that gives us about this flow rate, and therefore we want this kind of dose. We're going to dial in that. I mean, it would be a hassle, but you could dial in the coagulant and the polymer, and run it that way. It's never going to happen, though, Jerry, is it?
No, it's never happened.
Explain how the UV is going to get the flow, its control flows. What flow is it going to control off of?
It is, it's supposed to be programmed to subtract the waste backwash flow, and if the HCS system is running, it will subtract out the active flow waste as well. If the HCS system is not running, then we don't know, we don't have any flow here, and so we don't know what the flow is.
So
we
it
can't
requires
subtract
that
it
flow
out.
meter to be operational.
The only flow meter on the waste stream is going through the HCS system.
TIPS flow meter has to be operational.
Yeah, it's gonna be the.
Oh, if TIPS
either
flow meter,
Flow meter, right?
you're saying if that flow meter goes out, yeah, and I was saying you could still run active flow. Yes, you'd have to figure out something. I don't know what you do with UV.
Emmanuel.
Yeah.
No, Jerry, you got a spare, you take the one.
Like,
magnet,
from
you
the other
flip it
side?
across.
yeah, it would have been nice if they were the same size.
Yeah, they're different
One's
sizes.
4 inch and
Yeah.
one's 14
Yeah,
inch.
Yeah.
size them same.
Yeah, well,
meters in the spare parts box.
I'm just going off of experience.
yeah.
Recent experiences. Okay, bad.
Okay, so, and then the permit requirements for the future. What is it for the band screen? Don't look at your page. Oh, sorry, none for TIPS, none for band screen. What is it for active flow in the future? The idea is the filters, if you're going over the 5 G per square foot, would be 1.5 NTU, and this is the 24-hour average. There's other values as well. You'd be up to 7 GPM per square foot to get the 16.2. These values are the same, and then you got your 16.2 going out the other side. All right, that covers everything that I was planning to cover today. I don't know, I could talk a little bit more about active flow, and I've got a couple slides, but I think we're going to cover that in a separate session, so maybe that's enough for today. Any questions or?
Yeah, Paul, when are we going to get to the 16.2? When's that going to happen?
We
Trying to think who the most senior person here in the room is. Jeff, you want to?
Siphon tube.
Once you steal Livermore's water.
For a while?
I don't know the answer to that.
When can we produce it? If we have the effluent, when can we start producing 16.2?
Okay, so let's say that the regulatory testing happens this fall and winter. It's the process, like when Delta Diablo went through that process, it took them 2 years, but they were kind of on the front end of it. I would guess that the process might take a year, and so maybe it would be late 2019 where you could get approved for over 5 GPM per square foot, something like that.
So it's a ways out.
It is a process. I would say a year would probably be about what that would take. You got to do the testing, and then they review the data. And
And on that, getting the filters regulated to 7 gallons per minute per square foot, that's not something. Once we get that approval, we don't have to wait until the flow in the plant is 16.2. If we lost one of the trains or something like that, and we wanted to run at 7, we could do that.
Yes. And the idea is with the engineer's report, which is the regulatory report that goes to the regional board and the DDW for getting approval for the phase 2 project, is that both those numbers will be in there. The 12.3 will be in there, and the 16.2 will be in there, and it'll just say that we just so you can hopefully automatically go to go to the 16.2 as soon as that testing is completed, and not have to go back and do another engineer's report and that whole process. All right. Well, I hope that that you do end up feeling like this down the road. We'll see.
Thanks, Paul. Thanks, Paul. Thanks, Ron.